I'm Chris Sabol with Google, and this is Ross Stenfort with Meta. We're going to talk about flexible data placement and give an update on the state of the union. So FDP, flexible data placement, is all about managing write amplification and reducing it. So what is write amplification? Basically, when a host sends data to write to an SSD, it's the additional data that's written to the media. So it's defined as the data that's written to the media divided by the data that was written by the actual application. So for a simple example, this would be host writes a megabyte of data, the device writes in total 2.5 megabytes of data to the media. So that would be, a megabyte of the user data or application data plus another 1.5 megabytes of garbage collection data that's been garbage collected, and that results in a write amplification of 2.5. So why is write amplification bad? Well, it results in additional reads and writes, affecting QoS and performance and reducing latency and other bad effects. The media writes themselves wear out the device, and there's the additional power that goes along with needing to do those additional writes and reads. So if we had this world where you had a write amplification of 1, then really random writes kind of have the same performance as sequential writes. So, if you look at an SSD data sheet, you see this random write number, this sequential write number, they're very different. Well, if you can get those random writes to a write amplification of 1, then you'd have roughly the same performance. Whereas if your write amplification is 5, now you've got a significant reduction in your write throughput. So the history of improving write amplification starts way back with NAND-based SSDs, the early 90s. The solution, the only control we had back then was over provisioning, right? You have 8% OP, 20% OP, 50% OP. As you increase over provisioning, the write amplification naturally will go down. But it's expensive. So in 2007-8 timeframe, the trim hints were introduced, which allows the application to say, hey, I'm no longer needing this data, I've deleted a file, this can be reclaimed, which helped. And now, kind of 2022, we have TP4146 flexible data placement, and it's a hint to the drive on what data should be written together and placed together. So how did this happen, or how did it come to be? So at Google, we were interested. We identified write amplification as a major issue, major cost to us. We were looking for ways to improve it. We kind of surveyed multiple options and multiple strategies. We decided data placement on media is central, is the key. And we had this smart FDL proposal that we came up with. Kind of in parallel, Meta had a very similar journey. They identified it as a key factor to reduce, to control. They decided, just concluded that placement was key, and they had the direct placement mode proposal that they put together and working on. We sort of discovered each other, decided that...
We came up with the same conclusion and have similar problems and needs.
Yeah, and nobody wanted 2 different standards for this. So we worked together, we sort of, and with a bunch of other contributors, a lot of good ideas, and the result of this is TP4146. It's fully ratified. We've got a link down there to it, and we're very excited. So the high-level overview of FDP is basically, the host provides hints in write commands on to kind of where to place the data via virtual handle or pointer. On the device side, the device places data in blocks based on that hint, rather than just choosing a block based on, without any extra information. And it also has to advertise the size of those blocks so that the host knows kind of what the unit of the backing store is. A bunch of functionality doesn't change. Reads are not impacted at all. Deallocate trim works like it does. Security works like it normally would. Writes don't have to be impacted, but to get the hint through, you add this optional hint into your write commands. In terms of backwards compatibility, It can be, FDP is an optional addition to the NVMe spec. You can, it can be enabled or disabled on devices that support it. Applications aren't required to understand FDP to get the benefits. However, applications which have been extended with some knowledge of FDP can get incremental or additional benefits. Maybe I'll hand it over to Ross here. He's gonna, since I'm the software engineer, he's gonna talk, and he's the hardware engineer, he's gonna talk all about the software things, and I talk about the other stuff. So.
Hi, thank you, Chris. I'm Ross Stenfort at Meta, and we'll continue here on, the standard's great, but, it also requires open source software and an ecosystem to build this. So I wanted to cover some of the ecosystem topics. So the Linux kernel has been updated, so it has full I/O pass-through support. NVMe it also has full support. QEMU has full support. FIO support has been added, and I'm sure there'll be more support added to FIO in the future. NVMe CLI is a common utility used to manage drives. It has been updated. CacheLib is in the process of being updated. There's a pull request for that. And so what you see here is this was ratified in NVM Express in December. And you see very rapidly the open source community is embracing this and updating this and enabling this so we can all benefit from this technology. Here's some information on the Linux side. So it enables, how should I say this? So pass-through got updated, and so it enables a fast path through the I/O stack, and thus you can do pass-through now very effectively in the kernel. So quick summary of this here. It's been ratified in NVMe Express, the Linux kernel, NVMe, QEMU, FIO, NVMe CLI, and the CacheLib work is ongoing. So the ecosystem is ramping quickly. I know everywhere I go, I keep on hearing about different use cases for FDP. And so I encourage you to think about if you have use cases that can benefit you and how this would benefit you. And with that, let me hand it off to our next speaker here.
Hello, everybody. My name is Mike Allison. I work for Samsung. I'm a director of, senior director, and I work on standards. And I was the lead author of the flexible data placement. What that means is I did a lot of the typing, did some of the architectural work along the way. But this really was a collaboration between the customers that had a need, all the SSD vendors all contributed, the OS contributed, and it actually ultimated in the final TP, which got ratified. So things came from the OS sides, from the vendors, from the customers, and it was really a big collaboration. And if you pull the TP down, you're going to get a list of the key contributors to there. So it's an entire list. We're just up here representing it. I just want to say that we're not the only ones that did it. It was a real NVMe Express collaboration with the membership, and it was a lot of joy to work with everybody to do that. I have added all this stuff here. You just heard about all this, but I do want to apologize. I really wanted this presentation yesterday morning because you guys have all heard a lot about flexible data placement here. And it would be nice because a year ago we were here, the TP wasn't ratified, and we gave you an overview, but we couldn't tell you everything about it because we were doing the final stages of it. Now it's ratified. So now we're going to talk about the specifics. One of the things we argued a lot about, what should this thing be named? And you wouldn't believe in standards how much time that can take sometimes. But one of the key attributes of it is the backwards compatibility. And what that means is, make it really clear, is I could take a device that's shipped from the manufacturer with FDP disabled. You can enable it, plug it into a server that knows nothing about FDP, and it works and it behaves just like your conventional NVM drive today. Okay? As you do writes to different namespaces, it's going to mix them in on the media just like it does today. But now you can change your software at your choice and say, I want to take advantage of FDP, okay? And so it just gives you some flexibility when you look at the other things that were done before, like streams and ZNS. It gives you some flexibility where they didn't have that flexibility. And I have a slide here that'll go into the comparison, but I just want to let you know that I believe we don't get FDP without doing streams or ZNS to figure out where we want to be in between, and given that flexibility to the host and given the host resources time and when to make changes. So with that, let's go into the fundamental architecture. So fundamentally, we have a reclaim unit. And if you'll notice here, I do not have numbers on it because that isn't exposed to the host. But they do have, on the reclaim unit, the size is given to the host to say, I have these things that are backed by physical NAND, and here it is, and here's the size. One of the requirements on the SSD vendors is that size has to align with the erasing of erase blocks. So it could be one erase block or many. It could be here super blocks where you take a block from every die in there. It could be a super block. The architecture allows the SSD vendor to say, here's my FDP configurations that I support. So if you have a particular FDP configurations, then customer and vendor needs to work together to make sure that that gets created. One of the reasons we did that is, we have to test these devices from an SSD vendor. And if we have all of these configurations that we allow hosts to see or whatever, and we test them, but they use 5 and there's hundreds of capabilities, we want to test the 5 because we need to ship products. And what we're going to find is, I think as the ecosystem goes forward, we're going to align to a certain few key FDP configurations, but we want the architecture to be flexible so as time goes on, we can mature what the capability is going forward. Then we allow the reclaim units to be grouped into reclaim groups. And the architecture allows you to support one. So for example, if you're doing the super blocks like a normal conventional SSD today, they have one reclaim group and every reclaim unit is a super block. Okay? Or you could say, no, I want to have multiple reclaim groups and maybe I want to do a reclaim group is a die. So now I can expose the die to the host and the host can say where they want to write dies. But what comes with that is if you're writing all the dies, then you're required to distribute your data across the dies, because if you don't, endurance gets all messed up and we have to protect ourselves and whatnot. So the host can take some responsibility if they want, or you can let the controller do some of the responsibility of how to distribute the data within the device. So we get some real flexibility on both sides of how to go forward. Now we add these things called reclaim unit handles. And really what they are is the write resources to do writes. That's where we buffer data, because as writes come in, if a single LBA comes in and it doesn't align to the NAND write, we buffer it. And then once we collect enough LBAs from writes and it matches the way we write to NAND, then we'll write it to NAND. Okay? And so now what really happens is these reclaim unit handles have a pointer to a reclaim unit within each of the reclaim groups. The different handles, though, have to point to a different reclaim unit because that way they write to different sections of the NAND. Okay? Now, what we also did is there's this thing called an endurance group. And in NVMe, endurance groups been there for a while. Really what this is if typical SSD has one endurance group. It just says, this is all the NAND in my SSD. But I could create a device that I have 2 different types of NAND, put them in 2 different endurance groups. They're managed independently. They could have different FDP configurations, and I could still use FDP independently. I can enable them independently if I want. And so we just put this endurance group around it because what we're saying is the controller is going to manage the NAND in there because we still have to meet our warranties. We still have to do, and manage the endurance. If the host chooses to not do it, the device still has the capability of doing that. And I already talked about the FDP configurations, but the biggest part is we changed all the write commands, and the write command specifies which reclaim unit handle and which reclaim group I want that write to happen. That's the placement. And if you follow the link of where the reclaim unit handle is actually referencing which particular reclaim unit, that's where the write occurs. That's the hint. That's the placement. Okay? Now, the other thing is now I have these reclaim unit handles. And How do I use them? Well, at namespace creation, each namespace gets to say which reclaim unit handle I want to use. And it could say nothing. The backwards compatibility is I can still create a namespace and they say nothing about FDP and reclaim unit handles. The controller will give you at least one entry, and that's how we get backwards compatibility, because as the writes come in, we have a directive now that says where we put the reclaim unit handle and which reclaim group, and as the writes come in, we always use the 0th entry if you didn't tell me properly, so the device will do the write, and that's the backwards compatibility. But what namespaces can do is provide a list of which RUHs there are allowed, and now as the host does writes to that namespace, it can choose one of those 3 reclaim unit handles. Now, the reclaim unit handles can be in any order, whatever, so we actually have an index into them. So when the commands come in, we use the index, and one of the reasons there is if you're going to validate the command, we didn't want to have a sparse reclaim unit handle in the command. It would just say, hey, you were given 3 reclaim unit handles, and if you better be using 0, 1, and 2, or you have a bad command. So we wanted to make it simple. So from a host side, you just have a 0-based indexed reclaim unit handle that you're identifying with. So I am going to give you a demonstration of how it works, and before I do that, I have to explain everything that's there. So let's just say I have an SSD that's using super blocks, which means it has 1 reclaim group in it. We have 4 reclaim unit handles. These reclaim unit handles have a pointer to different reclaim units because they write to them differently. The reclaim unit 0, 2, and 3 are part of this namespace that was created for usage. And the red over here means that I have written particular ones here, and I don't know why that one should not be closed there, but oh no, I'm sorry. This one was written to completion, and RUH3 is pointing to an empty one. And this one here has some data already written to it. And RUH1 is not being used at this time, and it's pointing to an empty reclaim unit and not being used. Okay? So let's do a write command. And what I'm going to do is I'm going to focus, I'm an SSD guy, we're going to focus on the controller side, what happens. So when a write command comes in to the controller, it has a certain LBAs. The first thing it's going to do is go look at the new directive we did, and it's going to say, hey, I want to use placement handle 1, which is the index to which reclaim unit handle to use, and reclaim group 0, and it's the only reclaim group that we have in this example. And I did that because I wanted to save space. There's not a lot of room on a slide. And so what he's going to do is he's going to say, there's my reclaim unit handle that I'm going to use for this write. Now, if you go look at reclaim unit 2, and you go look at the reclaim unit handle 2, and you look at the reclaim unit 3 that it's currently referencing, there's not a lot of data left in that reclaim unit. So in this particular example, what we're going to do is we're going to take a part of that write and write it through the reclaim unit handle and the buffering, and it eventually goes out to the physical NAND, and it fills up that reclaim unit. It's filled to capacity. Now that write could be from any namespace. I just have one namespace, but if namespaces share a reclaim unit handle, it gets there and gets mixed there as well if you wanted to do that. But now, since that reclaim unit is filled to capacity, the controller automatically is going to go and pick a new empty reclaim unit handle to write to. This is one change from ZNS. ZNS, when you write to the zone, you always have to write to that zone. You can't go across the boundary. In FDP, if you keep writing, we keep writing. We'll go across the boundaries. Now, how do you get the write amplification benefit? Any of those reclaim units that are written to capacity, if the host manages the LBAs that were written there, and if the host rewrites those LBAs or deallocates those LBA, trim them entirely, when that reclaim unit needs to be used for future writes, the controller does not have to copy any valid data still left in there. All it has to do is erase the NAND and move forward. That's how we get rid of the write amplification. So if you're using FDP, you're managing the LBAs. What FDP gives you over streams is we give you feedback of, hey, how much data can you write to the reclaim unit that you're pointing to? Streams is you set it up once and it continues off. If you ever get off on alignment, you have no feedback, so you don't know if you're getting the benefit from streams. So that we realized we needed feedback. And the other thing here is you don't get errors, you always continue to write. Where in ZNS, if you tried to write over the boundary, you'd get an error. All right? And if you look at it from the controller side, we take the command, we pick the placement handle. If the host didn't tell me what the placement handle, I use placement handle 0. If they did tell me the placement handle, I know the reclaim unit handle. I know where I'm writing it. I update all my stuff, and I just take the next command and do it over and over and over again. The real neat thing is I can deliver an SSD today with one reclaim unit handle with FDP enabled, and you would plug it in, and it would behave as a conventional NVM SSD today. So I have the option as a vendor, I can just do FDP if I wanted to architect FDP and deliver it and give you the flavor, the old behavior, and give you the new behavior today. And I have this slide here. I'm not going to go through it. This is a comparison of streams to flexible data to ZNS. There's pros and cons on both ways. What you're going to see is flexible data placement and streams are identical in some things, and ZNS and flexible data are similar in some things, but they're all not the same. And I've covered the key points of this. This is available in the slides that will be available if you want to have that comparison. And so this is the end of my slide, and if you have any questions later, we're going to go ahead and go into the key per IO session, and then we'll take questions all together at the end. And so with that, here I'm going to let Festus come up here.